All right, welcome everybody. So we've set up and motivated what are called like the least squares solution to what is called the least squares problem. So just to recall the setup, I have a vector y, which oftentimes you might think of as an actual set of observed values of some response variable, like what is a country's wealth. And we have a data set that we collect, and we organize all of that data in a matrix A that we call, say, a model matrix. And from that matrix, we want to take a linear combination of the column vectors of matrix A using coefficients beta 1, beta 2, etc., that we organize in a vector of betas that we call beta hat. So we want to find values for these betas that are going to give us predicted value. So this A beta hat is my prediction for the, say, wealth of a country. And so the solution to this least squares problem is going to be a vector of betas that's going to make the sum of all of the errors squared as small as possible. So I have drawn one such point over here, and then we might have a whole collection of such points. But the idea is we have some subspace over here, which is formed by the column space of matrix A. And I have some observed value y, which in general may not be in that subspace. And I would like to find values for this beta so that my predicted value that I get, y hat, which I get by taking the matrix A times this beta, that these predictions are going to be as close to the actual value as we can get. And the way that we measure closeness is by looking at the complement to the orthogonal projection. So my prediction, y hat, that is the orthogonal projection of y into this subspace. And the corresponding error is the distance of my prediction to the actual value. And the solution to this least squares problem is going to be a vector of beta values of coefficients that we'll call beta hat that's going to minimize the sum. So I take this error and I square it, and then if I had another point, I would calculate that error and square it, and we add all of those errors squared together and then take the square root. And so the value for beta hat that makes this sum of all of the errors squared as small as possible, that's what we call our least squares solution. So let's try and figure out how we can find that solution. So we can first use the best approximation theorem, which tells us the best approximation for y, the closest approximation for y that sits in this subspace, is going to be the projection of y, the orthogonal projection of this observed vector y onto the column space of matrix A. And so this is going to be a vector that sits in the column space, which is closest to the actual value. So let's consider one such beta hat. Okay, so this is a vector of values for beta 1, beta 2, up to beta n, where n is the number of predictors that we might have in our model. So this is what we're going to use in order to figure out our predictions y hat. So we're going to take our model matrix, multiply it by these coefficients, and that gives us all of our predictions. And let's see what happens. So by the orthogonal decomposition theorem, we know that these errors over here, which we can write as y, the actual value minus the predicted value, these errors are the complement to the orthogonal projection. So these errors are all going to be orthogonal to the column space of matrix A. And so if the errors are orthogonal to the column space of A, then that means this vector of errors epsilon is going to be orthogonal to each column in matrix A. That's what it means to be orthogonal to the entire column space. So we're going to let bold AJ denote the jth column of that model matrix. And so as a result of that orthogonality, that means each time I take a column vector AJ with the inner product with the error term, right, we are going to get 0. because all of these sit in the plane and all of these are perpendicular to it. So this inner product we can rewrite as a product of two vectors, the first being the transpose of that column vector, just so the product makes sense. And then secondly, we take this vector that we get. This is the vector of epsilons, right? These are the errors. And so this gives us 0. By definition, these epsilons are perpendicular to the plane. And so since this condition holds for each column vector in matrix A, this means if we were to take A transpose, the entire matrix A, and take its transpose and multiply it by this vector of epsilons, we get a vector of 0. So we get the 0 vector. So we can rearrange this condition. I'm going to take A transpose times the vector y, and I'm going to take A transpose times A beta hat. So what we get is a condition that A transpose times y minus A transpose times A beta hat needs to give me the 0 vector. So I can take this product over here and add it to both sides, and we get the following condition, that the beta hat that's going to be the least squares solution has to satisfy this equation that A transpose A beta hat must equal A transpose y. Okay, so now we can generalize what we derived as the least squares solution. I'm going to change a little bit of notation so that we're consistent with the textbook, but we're going to actually change the notation back to working with model matrices and betas very shortly. But we can state these least square problems more generally beyond just regression. So more generally speaking, the set of least square solutions to this matrix equation AX is equal to B, and this could be any matrix A and vector X and B where the dimensions all make sense. So the least square solution is going to be given by the solutions to the normal equations that we just derived, which were that A transpose A times X, so the vector X that satisfies this equation, A transpose AX equals A transpose B. By definition, that is the least squares solution to this equation. And here we can see that we might have more than one solution to this equation. And it's going to be particularly nice when we're modeling to have unique solutions. So let's take a look at what conditions would be needed for us to get a unique solution to this least squares problem. So if our matrix A is m by n, so you might want to think about we have m observations and we have n predictor variables, then the following statements are all logically equivalent. That the least squares solution to the equation AX equals B is going to be unique, and that's going to happen as long as the columns of A are linearly independent. Since if the columns of A are linearly independent, then that's going to tell us that the matrix A transpose A is going to be invertible. And so if A transpose A is invertible, then we can multiply both sides of this normal equation by the inverse of A transpose A, and that's going to give us a solution that we can write out so that we've solved for X. So the least square solution we denote with a vector X with a hat on top of it. And again, in the case of regression analysis, these are actually our beta coefficients. So when we can find the inverse of A transpose A, then we can solve for X by finding this product A transpose A inverse times A transpose times B. So we're just multiplying both sides of these normal equations by the inverse of A transpose A. And this matrix might not always be invertible because the columns of A might not always be linearly independent. So let me just say that when you're doing observational data and you have a large matrix A of observed data, you'll almost never run into this issue that your columns there's going to be some linear dependence on your columns. But that does come up when you're running experiments sometimes, and if some of your variables are related to each other in a linear fashion, then you might not get a unique solution.